enantiomers, diastereomers, and meso compounds. And then just a last note, we want to ask respectfully that you leave any longer questions until the end of lecture so that we can make sure that we are getting to all of the points. All right, so I want to start off with a question and ask you all to participate by either answering aloud or by answering in the chat. Do you think that the two molecules that I have here on the screen are the exact same or different? And I didn't write it here, but you should know that they both have the same chemical formula, or molecular formula rather. Alrighty, so I see somebody said in the chat that they are the same in connectivity, but they're different in spatial arrangement. So do you feel comfortable explaining why you think they're different in spatial arrangement? If not, that's okay.
So they're different in spatial arrangement because in one of them, the CH3 molecule is on the right side, and the other one, the CH3 is on the left side.
All right, I like it. Thank you so much for being willing to give your opinion. In this problem, actually, what would happen if I were to take this molecule that's on the right and kind of turn it so that the CH3 is facing in the same orientation as in this molecule on the left? If I were to do that, these two molecules would actually look the exact same. We would have the CH3 over here, just like over here. This hydrogen that's on a dash would turn into a hydrogen that's sort of on a wedge, just like over here. And this hydrogen that's in a wedge would turn into the hydrogen on the dash that's back here. So these molecules are the exact same, and the only difference is that one of them is turned just slightly to, I believe, the right. Yeah, one of them is turned slightly to the right. But if I were to turn it again to the left, you would be able to, I'm sure, quickly identify they're the exact same. So now I have another question about another set of molecules. Again, these two both have the same formula, which I did not write here. Does anyone want to guess whether these molecules are the same or different? Well, this example is a little bit harder, so I'll go ahead and address it in the interest of time. These molecules are actually different from each other, because if I were to try and do the same thing I did for this example, which is to try and turn the molecule around a little bit and see if I can get all of the atoms to sort of match up in the same way, it's not going to work too well, mainly because of this carbon right here. We've got this hydrogen that's on a dash and this hydrogen that's on a dash. So if I were to try to turn this molecule around so that the oxygen is in the same place as this oxygen and this CH3 is in the same place as this CH3, the hydrogens aren't going to line up. So we're going to talk more about how we can tell whether molecules are the exact same or different, even if they have the same formula, and what makes them the exact same or different. So the molecules that I just talked about are what's known as stereoisomers. So I'm sure you remember from Chem 2070 that molecules that have the same formula but distinct structures are known as isomers. Examples of isomers include, for example, glucose and fructose. two different sugars that have the same formula but different structures and I believe different properties. So some types of isomers are structural or constitutional isomers. So either of these names is acceptable. And those are molecules that have the same formula but different connectivity. For example, if in this problem here, suppose I took the oxygen from right here in one of the molecules and I stuck it right here in the corner instead. And I just moved the carbon that was here and put it on the double bond instead. That would be an example of a structural or constitutional isomer. They have different connectivity. The isomers that I just showed you on the previous page are stereoisomers. And stereoisomers are molecules which only differ in the spatial arrangement of their atoms. So we can have two different types of stereoisomers. We can have chiral molecules, which are molecules which can be differentiated from their mirror images. So whenever I say mirror image throughout the lecture, I want you to just imagine that we have a set of two molecules and I'm drawing a dotted line which represents a mirror between them. So if one molecule was looking in the mirror, its mirror image is what it would see as in reflection. So if a molecule can be differentiated from its mirror image, then it's what's known as a chiral stereoisomer, and it's said to have chirality. An achiral stereoisomer is a molecule that can be superimposed on its mirror image. An example of an achiral molecule is these two molecules right down here. If I were to put, let's draw another mirror, and let's imagine again that this methane is staring in the mirror, and this is what it sees in reflection. These two molecules can be superimposed on each other. I can take this hydrogen and put it right on top of this hydrogen. I can take the hydrogen on the dash and put it right on top of the hydrogen on the dash. They're the exact same and they're superimposable. So they're said to be achiral. This chart just demonstrates what I just said. We've got our broad category of isomers, which are molecules that have the same formula but different structures. Then we have our constitutional or structural isomers, and here's a great example of that. These two molecules, this one up here and this one up here, they both have the same formula, but you can see that the structure, like this molecule is on the end, and this molecule, the fluorine, is kind of the middle part. So they're both have different structures. If the molecule has the same formula, same structure, and the only thing that's different is the orientation of the atoms, it's going to be a stereoisomer. So we're going to go ahead and talk about different forms, again, of stereoisomers, which, remember, they can be chiral or achiral, but some of them have names, enantiomers and diastereomers. We'll talk about them later.
Wait, I have a question.
Okay.
So not all isomers are exactly the same.
Right. Some of them are constitutional isomers, and some of them can be stereoisomers. So
the stereo ones, they're exactly the same, right? Like with each other.
They're same in terms of connectivity, and they're same in terms of molecular formula, like all the isomers. Or all the isomers are the same in terms of formula. Stereoisomers are the same in terms of formula and in terms of bond connectivity.
But they have the same exact structure?
Yes, they have the same structure. The only difference is that the atoms may be oriented differently in space. For example, down here, this is an example of a type of stereoisomer. It's got the same bond connectivity and the same structure, but the atoms are oriented a little bit. Like, let me go ahead and draw both of these molecules. They're shown just like one molecule, this one is looking at itself in the mirror. Let me go ahead and turn this molecule around so you can see more how this is. And now I'm going to draw, that's this one. I'm going to draw the second one. So can you see more clearly how this structure is, this molecule is different from the previous image? These are both a type of stereoestimate that we're going to talk about in just a moment. But for now, like, you can just tell that they're different molecules. They're not the same. So before we talk about different types of stereoisomers, I wanted to go over some important definitions. So we have a stereocenter, which is an atom where changing any of the two attached groups changes in configuration. And when I say configuration, just know that changing the two groups can create a different molecule or a molecule that's not the exact same. Stereocenters are most often carbon, but they can also be atoms like sulfur or nitrogen, but they're most often carbon. You can find stereocenters in alkenes that have this carbon-carbon double bond right here, or you can find them in alkanes, which have a carbon-carbon single bond. So below, I have two different atoms that have stereocenters. This is an alkene, and you can see that if I were to move either of the two groups on this carbon right here, or either of the two groups on this carbon right here, I would be able to get a molecule which is different from the original molecule. So normally we show that a atom is a stereocenter by adding an asterisk. So I'll go ahead and add an asterisk next to both of these two carbons, because if we were to switch the, move this CH3 group up and this H group down, we get this molecule over here, which is not the same as this molecule. These two are stereoisomers. And the same goes for this molecule right here. If we change the orientation of two different groups, in this case, they moved around the C2H5 and the C3H7. I'm going to shade those different colors. And then look, in this version of the molecule, which has the same molecular formula and the same connectivity, we moved the C2H5, and now it's on the wedge. It was on a dash over here, and we've moved it, so now it's in the wedge. It's coming out towards us. And we have moved the C3H7, which is on a dash. The C3H7 was on a wedge, but now it's on a dash. So we have switched the two attached groups, and these two molecules are not the same. So that's why I'm going to go ahead and give this central carbon an asterisk, because it's a stereocenter. Our next definition is a chiral center. And you might hear the following terms used instead of a chiral center. Chiral carbon, asymmetric carbon, or asymmetric center. I brought these three alternate terms up because you might hear your TAs using them, or you might hear them used in other lectures in the week, and I didn't want you to be confused. All four of these are the same thing, except for, of course, the chiral carbon and the asymmetric carbon specifically refer to carbons, while just the broader term chiral center, asymmetric center, can be an atom, frequently a carbon, but again, could be like a sulfur or a nitrogen. And it's surrounded by four different groups. So remember, in our example that we just talked about up here, the example on the right, this carbon these two carbons with the asterisk are both stereocenters, as we talked about, but they are also chiral centers because they are surrounded by 4 groups which are not the same. We have an H, a methyl group, a C2H5, and a C3H7. So that's 4 different groups. Now, if I had a carbon that looked like this, where we have a hydrogen, I'll add a methyl, and I'll add bromine, is this carbon surrounded by 4 different groups? You can answer out loud or you can answer in the chat. Great job. I'm hearing people answer, no, it's not the same type of, this carbon is not a chiral center because it's not surrounded by 4 different groups. So, great job.
All 4 of them have to be totally different.
Yes, all 4 attached groups have to be different for it to be an infinite carbon. So in this example, all 4 groups are completely different. In this example, we've got 2 hydrogens. If I were to make one of these groups different, then this carbon would be an asymmetric carbon. Now, in our other example, where we had 2 stereocenters in this molecule, it's important to note that these carbons are stereocenters, but not chiral centers, because they are not surrounded by 4 different groups. These carbons are only surrounded by our H and our CH3. We don't consider like the group that's connected by the double bond. It's only like, I believe, these 2 groups here. So these carbons are considered stereocenters, but not chiral centers. And then just an aside, which will be more useful later on in the lecture and later on during the week, having a chiral center is neither necessary nor sufficient for chirality in a molecule. And that just means basically that some molecules which are achiral may have a chiral center or a chiral carbon. We will talk more about those examples a little bit later, but just keep that in mind. So I'm going to go ahead and demonstrate using my model kit that the example on the right is 2 molecules that are not the same. So I'm going to have to turn screen sharing off to do that. So I invite you to go ahead and take a screenshot after I assign colors to each of these groups. I'm going to make the hydrogens, you're going to see them represented by the green bulb that's on the model kit. The C3H7s are going to be represented by the blue. The C2H5s are going to be represented by the red. And I'm going to make the CH3 groups, the methyls at the top, represented by the white. You can go ahead and take a screenshot of that, because I'm going to go ahead and turn screen sharing off in a moment. Alrighty. Let me turn my video on. And can you all see the 2 model kits that are on the table? Yes. Yes? Okay, wonderful. Well, for our 2 different models, we have our green hydrogens that are sticking out in front. Those are right here. We have our blue CH3H7s that are sticking out in the back. And we have our red C2H5s, those are over here. And we have our white methyl groups at the top. again, I want you all to imagine that we have one molecule that's looking in the mirror. My hand is the mirror. And then this molecule is what it sees in reflection. So these two molecules are mirror images of each other. Now, a test that we can do to see if the molecules are chiral or not is to try and superimpose the two molecules on top of each other. So what I'm going to do to prove that these molecules are not the exact same is I'm going to turn this molecule over here and see if I can get all the colors to line up. Now remember, these two molecules are mirror images. So I've got, if I put them like this, can you all still see? Okay. If I line them up like this, I can have my two red C2H5s. Those are lined up nice. That's great. I've got my two white methyl groups lined up nice. That's wonderful. But as you can see, I can't get the hydrogens, which are green, and the C3H7s to line up properly. So this indicates that our molecule that we just talked about is not superimposable on its mirror image. So a term we could use to describe this molecule is chiral, because it's not superimposable on its mirror image. And as we mentioned earlier, chirality is not necessary or sufficient. I'm sorry, having a chiral center is not necessary or sufficient for chirality in a molecule. So I know I talked about how these molecules, the carbon that's right here is an asymmetric carbon or chiral carbon or a chiral center, whichever name you want to use. That's not what specifically makes this molecule chiral. What makes the molecule chiral is that it's not superimposable on its mirror image. It happens to have a chiral center, as chiral molecules frequently do, but that's not what makes it chiral specifically.
Wait, so what makes it chiral?
What makes this molecule chiral is that it's not superimposable on its mirror image. Most chiral molecules, well, many to most chiral molecules have a chiral center or an asymmetric center, but that's not what makes it chiral, if that makes sense. Alrighty, so we're going to go on and talk specifically about the type of stereoisomer which we were just referencing. So if you remember, the two stereoisomers that I just had were non-superimposable mirror images, and those are known as enantiomers. Enantiomers are chiral. So just as our example before showed, again, the definition of chiral is an object that is not superimposable or distinct from its mirror image. So enantiomers, by definition, are chiral enantiomers. Or, I'm sorry, are chiral stereoisomers. Like, it's the dictionary definition, I believe, of chirality, differentiated from its mirror image. And stereoisomers are not superimposable on the image. So, an example for chirality, which you might not have thought of before, is your hand. So I invite you all to take your hands and put them up in front of the screen. And you might not have thought of this before, but your hands are actually mirror images of each other. If I were to go and stick the mirror right between my two hands, and put this hand, imagine putting this hand in front of the mirror, I would see this hand, well, my hand would see this hand as its reflection in the mirror. Now, I'm going to try and superimpose my hands, just like we did the molecules in the model kit, and see if I can get them to perfectly line up. So if I go like this, then you can see that I've got my thumb sticking out on both sides. So just as we couldn't get the blue and green atoms on our model kit to perfectly line up in the example before, you can't superimpose your hands. You've got the thumb sticking out. You've got all the different fingers lined up together. It's not gonna work. So your hands are chiral, and the term that you can use to describe them, if they were stereoisomers, is enantiomers. So whenever you have two molecules and you're trying to figure out, are these enantiomers, are these chiral, think about your hands. That's what I like to do sometimes. I think it's kind of cool. Another kind of key aspect of enantiomers and chiral molecules is that they cannot have a plane of symmetry. And when I say a plane of symmetry, you can't draw, I'm gonna go ahead and draw one through this molecule. You can't draw a line anywhere through the molecule and have both sides be completely equivalent. For example, that was not a good one. If I were to draw a line through this molecule, is this half on top equal to the half on the bottom? No, they're completely different. We've got this group up here and we've got this group down here. They're not the same. So that's another way you can show that a molecule is chiral, or that molecules might be in relation to each other, enantiomers. They don't have a line of symmetry. And if you look at your hands, if I were to try and draw a line straight through my middle finger, the sides of my hand would not be the exact same. So that's another indicator. My hand is chiral and my two hands are enantiomers. They can't have a plane of symmetry. So now let's go ahead and talk about some other types of stereoisomers. So we've got diastereomers. Those are stereoisomers with at least, I'm going to go ahead and underline this, 2 stereocenters, which are non-superimposable, non-mirror images. So I'm going to go ahead and create a molecule that has 2 stereocenters, so you can see what it looks like and visualize it. So this is a molecule that has 2 stereocenters. We've got our carbons that are in the center, and if I were to change the orientation of 2 different atoms on it, so if I'm going to change the blue, put the blue group where the green group was, I'm going to put the green group where the blue group was in the back, that changes, that makes this molecule that I'm holding up different from the one that I was holding up a second ago. So we have 2 different stereocenters, which are the central carbons kind of here that I'm pointing to on this molecule. And molecules with at least 2 stereocenters, which are non-superimposable, non-mirror images, are diastereomers. I'm also going to note that diastereomers are chiral. And we'll talk a little bit more about classification of diastereomers later on. So another molecule which also has at least 2 stereocenters could be a meso compound. Meso compounds are achiral stereoisomers which contain at least 2 stereocenters and have a plane of symmetry. So this is important. As we discussed earlier, chiral molecules and enantiomers can't have a plane of symmetry. So if a molecule has at least 2 stereocenters and it has a plane of symmetry, it has to be meso because it's achiral. I'm going to go ahead and create a meso structure for you all. So this is what a meso stereoisomer for this molecule would look like. I've got our two white bulbs up here, and I've got our green ones in the front, and I've got our blue ones in the back. Can anyone tell me either out loud or like in the chat where a plane of symmetry might be on this meso compound or meso stereoisomer?
Between the bonds of carbon?
Yeah, between the sides of the carbon. So if I were to take a line and draw it right between this central carbon bond, I would have 2 sides of the molecule that are the exact same. So unlike your hand, this molecule has a plane of symmetry, even though it has 2 stereocenters and I believe 2 chiral carbons. So this could be an example of what we're trying to say when we say that chiral centers or stereocenters are not necessary or sufficient for chirality, because this molecule right here is achiral due to the plane of symmetry that it has. All right, so here's this. And then lastly, this isn't a definition, but it's a formula below to determine the number of stereoisomers using the number of stereocenters that we have. So for this molecule, I'm going to count up the number of stereocenters we have, 1, 2, and to determine the number of stereoisomers that we could form, I'm going to take 2 up to the number of stereoisomers and get 4 stereoisomers total that we could make using this molecule. So this is just a good formula to remember, because for some problems, they ask you to draw out the number of stereoisomers or draw out stereoisomers. So if you remember this, you can quickly calculate how many you're supposed to draw.
So the only difference from the meso and the diastereo is like the meso have a line of symmetry. Exactly.
Well, almost exactly. Meso compounds, the most important thing that I want you guys to remember right now is that they are achiral. They have at least 2 stereocenters, and they have a plane of symmetry. The diastereomers, they are chiral, and they're non-superimposable, non-mirror images. I know that's a lot to take in, but we will definitely try and go over these terms as much as we can during study group and homework, so you guys really get to internalize the definitions.
I'm confused with chiral and achiral now. What's the difference with chiral and achiral?
If you want to hang around until the end, we can definitely go more into depth with chiral and achiral. But I want to definitely make sure that we get through all the lecture content, just because some people might need to leave right at 12.
Okay, that's fine.
So I'm going to go ahead and draw out our 4 different stereoisomers for this molecule. So first, we have the one that I'm drawing right now with our 2 white, the W stands for white, our 2 white atoms sticking straight up. We've got, let me turn it around so then it's actually true. We've got the blue ones coming out towards you, and we've got the green ones going back behind. This compound is meso and achiral. It's got a plane of symmetry right there. The 2 sides are completely the same. So this one is achiral. Now I'm going to go ahead and draw the other 3 stereoisomers for the molecule. We can have one where we have the green for one side facing up. We can have the blue in the back, the white one coming forward. And then we can have the blue one facing in front. This is another stereoisomer for the same molecule. I'm going to draw the 3rd one, or a 3rd one, I should say. Because you can give these in any order. You don't have to, there's no specific order for drawing them. White one in the back. This is a 3rd one, and now the last stereoisomer for this molecule. So again, remember that the blue, the white, and the green, those are just like the first name for each color of like the little balls on each of the atoms in this model. This meso one is the only stereoisomer here, I believe, that is achiral. The other ones are all chiral, and we will talk more in the week about how to show the relationship between these 3. And now I'm going to pass it over to Samantha.
Thank you.
I actually have a question real quickly. So for the meso compound, does it mean only one of the structures could be achiral and then the rest could be chiral? Like the example?
Well, you could have an example, I think, where you have more than one achiral stereoisomer. This molecule just has one achiral or meso stereoisomer. But I think you can have other examples where you have more than one achiral stereoisomer, I think.
Okay, thank you.
This number of like stereoisomers, like the 3 chiral and the 1 achiral, that's just specific to this molecule. So, like all of them can be different. All the molecules.
Are there any other quick questions before we move on? All right. So now we're going to talk about optical activity, everyone's favorite topic. So optical activity is going to be something we measure using polarimeter. And a polarimeter is just going to be this thing down here. Just looks like a blue cylinder. But basically, I'm going to go over very briefly and not very thoroughly how polarimeter works because it's honestly not super important. But usually you'll have like a synthesis reaction or something, you'll have some products, and you want to figure out if they're chiral or achiral. So what you do is you take your products, you load them into, this pencil will turn on, to this polarimeter, and you're going to shine plain polarized light, which is just light that is traveling in one plane. If that doesn't make sense, don't be super worried. If you're really curious, you can email me about it. So you're gonna put this plain polarized light through. We abbreviate it PPL. And it may either rotate the light or do nothing to the light. And so here's where you wanna pay attention. The chiral molecules are going to rotate the light. And so we call them optically active. And achiral molecules will not rotate it. So they will be optically inactive. And so polarimetry is honestly just used as a good way to differentiate between chiral and achiral molecules. And so something that is interesting to note is that enantiomers always come in pairs, like we talked about. And so one of the enantiomers, and I hate this word, called the dextrorotatory enantiomer, is going to rotate the light in the clockwise direction. Let me highlight that for you. And the other one, level rotatory, is just gonna rotate it the opposite direction, which is counterclockwise. And so the observed rotation of the plane polarized light is gonna depend on a lot of things, including like cell length, temperature sometimes, specific rotation. Don't be super worried about this. Gannon will go over it more. And honestly, it doesn't appear on more than like one question on the exam. I will give you the equation really quickly just in case anyone's interested. You're going to see this later though, and we're not really going to test on it in this summer course just because it's not a big subject. But here it is if you're curious. So this alpha in brackets is going to be the specific rotation of the plane polarized light. That's just going to be measured in degrees. This alpha observed is going to be the observed rotation. So the rotation of the light after it comes out the polarimeter. C is going to be the concentration of your isomer. And L is going to be the cell, the path length, so how far it has to travel. So again, Gannon's going to talk about this more when you take his class, but just be worried mostly with chiral versus achiral, and if it means it's optically active or optically inactive. Does that make sense? I'm going to keep going. Now we're just going to have a bunch of practice to go over what we talked about earlier. So first thing here is going to be, are these molecules the same? So this here is going to be D for deuterium. If you remember from Gen Chem, and this isn't so important, deuterium, D is just going to be an isotope of hydrogen. I believe deuterium is 1 neutron, 1 proton. You don't need to memorize that, although sometimes it will come up. And H is just going to be 1 proton, I believe. I'm not going to write that because it's on the pentagon. So sometimes you will see Ds in orgo, and so just so you know, it's deuterium. And so what we want to do to see if these molecules are the same is to think about chirality. So usually our chiral centers are going to be carbons. We want to look for something that has a bunch of different groups. So immediately our eye is probably drawn to this carbon, the one that I highlighted in blue. Let me do it in red. There we go. It's got this D and it's got this H. And so we want to say this is chiral or achiral. Does anyone remember the difference between the two? Okay, so the main difference is just going to be that chiral molecules can be differentiated from their mirror image, whereas achiral is going to look the same. So if we want to draw this out again, I'm just going to draw it down here. Let me know if this is too small. Is this going to fit? Yeah, this will be fine. I'm just going to ignore the H like we tend to do when we're drawing skeletal structures. You're going to see that these mirror images look the same. So this guy is going to be achiral. And what does this mean for the problem? That means that these two molecules are actually, these two molecules are actually the same, because if you imagine we look back down at our mirror, the deuterium here, it has not a wedged line, it has a dashed line, so it's going into the board, but it could just as easily be going out of the board. Anyone have questions?
I don't see, you didn't draw the other thing going in the back.
Yeah, wait, can you say that again?
Because there's like 2 wedges, and like you want to draw 1 wedge.
Let me look at my Zoom. Is it not sharing? But basically, are you talking about the 2 structures that I drew down here?
Are they not they're not the same from what's up there? Like,
no, these 2 are just going to be mirror images, hence why they're both dashed lines.
okay, it's just
imagine, yeah, if you can imagine, this is really the only thing, this deuterium is the only thing differentiating this pentagon. So even though it's sticking into the board, in this case, it could just as easily be sticking out of the board here. I can draw this guy. This guy, you can also draw him like this. So it's ugly. Does that make sense? So because this deuterium is really the only thing differentiating it, you can just imagine flipping the pentagon over, and then the deuterium is now sticking forward instead of back. Does that help? If you have any questions, you can just email me. So next practice is this molecule chiral. If you remember again, chirality, in most simplistic terms, is just going to be mirror images that are different. And so remember, chiral molecules usually, but not always, have a stereocenter. And what a stereocenter means again is that if you change to the attached groups, let's hit an N, here we go. You change the conformation of the molecule, or you get a different conformation. So if we want to see if this guy has a mirror image, we can go, here's my mirror, just flip them over. No, I'm too close, there we go. So can anyone tell me, either in the chat or just shout out, whether these 2 are different? I actually cannot see the chat, but hopefully someone got it. If not, that's totally fine. Basically, these 2 molecules are going to be the same. So are these different? Let me write this. No. So we're going to call this achiral. Or to answer the question, no, it is not chiral. And so we can also look at the stereocenter if we wanted to. Carbon is usually going to be the stereocenter. We're going to look at him. We're going to say, if we change two of these attached groups, is it going to give you something different? Not really, because you see these three hydrogens are all the same. So the most you could do is maybe move the bromine around, this guy, and one hydrogen, but that's going to give you the exact same molecule. Does that make sense? So our next practice is going to be a throwback to optical activity. So does this molecule down here rotate PPL? Remember, PPL is just plain polarized light. I'll write that. And if you remember from the other slide, chiral molecules are going to be the ones that rotate PPL. Achiral do not rotate it. And so what we want to do is figure out if this guy is chiral. So let's think about it. Does he have a stereocenter? How many different groups are there? There's 1, the hydrogen, 2, the methyl, 3, the fluorine, and we gotta change colors, 4, the bromine. So this guy is going to have 4 different groups. So is he a stereocenter? Yes. Because if you remember, a stereocenter only requires that changing two of the groups changes the conformation. And something else you can think about is if he's a chiral center. And the way a chiral center is different, if you remember, is that chiral centers are going to have 4 different groups. So because this is also fulfilled, it is also a chiral center. Something that might help you is that, kind of like squares and rectangles, all chiral centers are stereocenters. But not all stereocenters are chiral centers. Oh no. Because if you remember, stereocenter only requires changing 2 groups, whereas a chiral center would be 4. And so, almost there, don't worry. How many stereocenters are in this molecule? So we just talked about it a little bit. Stereocenter is going to be 2 different groups. And so if you look at this guy, it's first carbon, stereocenter 1, second carbon, stereocenter 2, because if you see, they're each going to have 3 different groups. I don't know why I labeled it like that. So in this case, they are also chiral centers. And so just as a little review, I'm going to take this methyl guy out. I'm just going to put R for the rest of the molecule, hope that's okay. And so we want to think, okay, well, this guy has 3 groups. Why isn't he a chiral center or stereocenter? So again, he has 3 groups, but all these hydrogens are the same. So it doesn't really matter if you change 2 of the groups, you just end up with the same molecule. So this is not a stereocenter or chiral center. Okay, so this is gonna be the last practice problem for today. So you're gonna see these 2 molecules. We're gonna go, are these enantiomers, diastereomers, or the same compound? And so let's remember the definition for all these. So the same, of course, is just gonna be the same. Enantiomers will be non-superimposable mirror images. Diastereomers are going to be also non-superimposable. But they're going to be non-mirror images. So that's generally the main way you're going to differentiate between enantiomers and diastereomers. So a pair of enantiomers is going to be mirror, a pair of diastereomers, non-mirror. And so let's go ahead and look at diastereomers and enantiomers because those are what we tend to have when we have these problems. And so let's imagine there's a little mirror here, the blue dash. And so right away, it looks like these two could be mirror images because you see you have the hydroxyl group on the line, same over here, hydrogen on the dash, and then the methyl group on the wedge. And so we're like, okay, they're mirror images. But what? If they're mirror images, they cannot be diastereomers. So we're going to go ahead and cross that out. And something else you want to check real quick is to see if they're the same molecule. So I'm going to say, check to see if they're meso. Remember, meso compound is going to be something, two more. Stereocenters, if I can spell stereocenter correctly. It's also going to have a plane of symmetry. And they're going to be achiral, which means they will not have an enantiomer. So meso compounds, they don't come in pairs or anything. They're just going to be, whenever you have a meso product, for example, which will make more sense in later lectures where we talk about those reactions, you're only going to have that one product. He's not going to come with a friend. So right now, it looks like we have mirror images, but let's just check to see that they're non-superimposable, because remember, that's necessary in order to have an enantiomer. So this is where it gets a little bit tricky, because originally, I turned this guy around this way. This is an easy mistake to make. Let's put the hydroxyl on the left. And if you turned this guy, I don't have a model kit to show you, unfortunately, but just imagine him moving forward and then to the left, and then this hydrogen is going to go swoop right over here, and that will become the new wedge, and the new wedge, and the dash, and the dash, and all the dashes are going to be CH3s. I'm just going to draw them in just in case. And you're going to see immediately that this guy does not look like this guy. You have the hydrogens on a wedge, hydrogens on a dash over here. Same thing with the methyls, they're on a dash here and on a wedge there. And so you might think, okay, they're enantiomers, but remember that you want to think about treating them every way you can, essentially. So I'm going to imagine turning both of these guys by 180 degrees. And when you do that, you're actually going to see the following. This guy and that. Ooh, that doesn't look like an H. And you're going to have the other one. You're going to see that they look exactly the same. Now let's make sure this makes sense. So we moved this OH kind of down this way. So I'm just going to highlight. Let's do this OH became this OH on the left. This top OH became this OH on the right. Hopefully that makes sense to everyone. And so you still keep the wedges for the methyls and the dashes for the hydrogens. So you're actually going to see that these two molecules are the same, despite the fact that turning this guy this other way seems to make him look different from his friend. So that's something you want to be aware of, which way you're turning the molecule. If we were to imagine just flipping this guy upside down, what was I saying? Yeah, so you're actually gonna see that these two guys, like I said, are the same. Same molecule. And so they're not enantiomers. This is just would be a meso product, for example. And so something else that you can use to check to see if you have meso is to look at your plane of symmetry. So remember, meso compounds are always going to have a plane of symmetry. So you're going to see right here, both of these guys have a plane of symmetry, which makes sense because they are the same molecule.
Alrighty, can you guys hear me? Perfect. So some advice that I would have for Stereochem is to try making flashcards on apps like Quizlet to help memorize definitions. I have used flashcards on Quizlet a lot for studying, so if you want a set that's pre-made, you honestly can just use mine. Just let me know after lecture or send me a message and I can hand you the link. It's very important to have these definitions memorized so that you can effectively solve the problems. For example, if you keep getting the definition for chiral and meso mixed up, or the definition for enantiomer and diastereomer mixed up, it's going to be really hard to solve the problems. So the sooner you can get that kind of nailed down, the better. I also really liked writing the terms out and focusing on how the definitions are related. Like, for example, how is chirality related to being an enantiomer? How are enantiomers related to diastereomers? So writing things out, because I think I learned by writing things out, is definitely a great idea to sort of process the information and remember things. And then lastly, doing lots of practice problems is a great way to be able to master stereochem, especially because you'll start to notice that there are only so many different types of molecules that we can give you now and GANM can give you like kind of in the fall. So sometimes on a test, I wouldn't know exactly what the correct answer for a stereochem question was, but I would think back and be like, I saw an example that was just like this on a practice problem that I did a little while. And I remember how I did that one. I remember that even though this certain carbon looks a certain way, maybe this problem looks like it's chiral, I remember from practice problems that it's actually achiral. And doing those practice problems helped me to develop my critical thinking skills and be able, I think, to perform better on the test because I had some examples that I could reference in my mind. So, Sam, do you want to talk about your memes for stereochemistry?
I found these while we were doing the presentation, so enjoy. Hopefully they make more sense now. The end.
Reminder that the L and the D at the bottom, that stands for, oh gosh, I'm gonna mess this up. Laboratory and dextrorotatory. Those terms refer to two enantiomers that are chiral and achiral. And like the terms are used to describe, if you remember, how the enantiomers rotate plane polarized light. So there's that. So now we would like to open the floor up to you guys because we know that lecture is over, but you guys may have questions. So we are able to stay and kind of talk about stuff if you would like.
I have a question.
Okay.
Yeah, I was wondering how, what's the procedure for deciding if, two molecules are the same or different?
That's a very good question. I don't want to give you like an algorithm because a lot of these questions are, like a lot of the molecules you'll see are sort of different and you might not have to follow all the steps every time. Just basically, I would want to see like, can I kind of superimpose the molecules? So you are allowed, just so that everybody knows, to have a model kit on the exam. So some people like to build up the actual molecule if they can and see if they can superimpose it that way. You want to check and make sure, because sometimes it's tricky, as you saw in the example Samantha did. Sometimes you might have to pancake the molecule over and then superimpose it, and it turns out that they might look different, but they're actually the same. Sometimes you have to rotate part of the molecule, as you did in the challenge problem, and then you can see, oh, it's the same, it's not the same. So always try to remember to do that. And then generally, if you can superimpose the molecule, when I say superimpose, I just mean like you can kind of align the two molecules and they look like they're the exact same. Like this is kind of a bad example because these two are not superimposable at all. But if I were able to like get all the atoms on this molecule kit to line up perfectly, that would mean they're superimposable. And if you are superimposable, that means you're basically the same. So if you can superimpose two molecules on top of each other, then it means that they must be the same molecule. Yes, you're allowed to have a model kit with you on the exam for both our exams. If you happen to have a model kit, don't feel any pressure to like go buy one just for this course. But you're also allowed to have one for Ganam's course during the fall. And I will be posting like the type of model kit that I have. And since so many people are interested, I will post a link to my Quizlet set for stereochemistry as well. And those will be available on Canvas, and I'll link them in the description on YouTube below for those of you who aren't enrolled in the course.
Do you have a question, Amber?
Yeah, I was wondering if you could like explain again the definition of the diastereomers. I'm not really sure how or like why the non-mirror image is can be chiral.
Do you have an example with me? I don't have a practice problem, but
I'm trying to see if I can create a diastereomer real quick with the model kit so that I can show her visually.
Okay, diastereomer, non-mirror. So chirality, basically, if you remember, if something has a chiral center, that can be just mean 4 different groups. Here, let me share. Hopefully this helps. What do I want? Yeah, let's do him. Okay, so basically, yeah, in something like this example, this has a chiral center, right? Yeah, it has 4 different groups. And so, I'm trying to think of a diastereomer question. So your question was, how are diastereomers different from enantiomers, or?
It's like I guess more like the definition of chiral, because how a non-mirror image could be chiral.
Yeah, so molecules on their own can be chiral, like for example, if they have their own chiral center. But I should find a diastereomer question. But if they give you 2 molecules that are non-mirror images but are on their own chiral, then they are diastereomers. Does that help at all? I can try to find a better example.
And just another like aside, we will be talking a lot more about configurations and like specific configurations a little later on in the week. So it will be easier for us to explain more about diastereomers, and also it's easier for you to like tell which 2 molecules are diastereomers of each other after we have that lecture. So as for now, the main takeaway for diastereomers is just that they're non-superimposable non-mirror images.
I think
we will talk more about how to tell what's a diastereomer a little bit later on in the week.
Okay, I think I might have thought of one. I'm like doing this off the top of my head, so Sydney, please correct me if this slips whack. But let's say we had these 2 molecules. So for the most part, sorry, let me finish it. For the most part, oh no, that is not supposed to be chlorine. Bromine, for the most part, now they look the same. You can have the chlorine up top, bromine on bottom. And so on their own, are they chiral? Anyone can answer this. So on their own, they are going to be chiral. You can look for the stereocenters. But if you were to try to put a mirror between them, they are not mirror images. Does that make sense?
Can you explain why they are chiral?
Yeah, so chirality is going to be dependent on having a mirror image that is different. If they give you two molecules, how do I explain this? So I know a lot of the times in this lecture we've been talking about things as if they're in pairs. So something like an enantiomer is always going to come with a buddy who's their enantiomer, so that always comes in pairs. But chirality is something that is an individual, what do you call it, trait. Did that make any sense? I don't know if you have a better, do you have a better way to state it, Sydney?
I would describe chirality kind of the same way and just say that, like, if you're trying to tell whether something's chiral, the best way to do that is to try and draw up an imaginary mirror and draw out the molecule's reflection, like what would that molecule see in the mirror, and then see if you can superimpose the mirror image on the original molecule. And if you cannot superimpose them, that means the that means the original molecule is different than its mirror image and it must be chiral.
Yeah, so like Sydney said, this molecule would be chiral because if you draw its mirror image, it's not going to be superimposable. Like, there's no way you can flip this guy around that makes him look like him by mirroring. Except the only place we're going to see diastereomers is if they give you a question where two things aren't mirror images to begin with. So I know in a lot of the problems we've done, let me find one, like the things we gave you were mirror images, but that might not always be the case.
Yeah.
Does that help? Sorry if that's confusing. Stereochemistry back.
Yeah, that was helpful. Thank you.
Anyone else?
I have a question about that formula that you wrote. What was that for?
Oh yeah, let me go back to it. Honestly, do not be super worried about it if you're talking about the polarimetry, I'm guessing.
Yeah.
Yeah, Ganem will talk about it when you take his class, but it's basically specific rotation of the, turn my pencil on, specific rotation of the plane polarized light is going to be equal to the observed rotation of the plane polarized light over the concentration of the isomer, whatever you're using, times the cell length. You can write it down if you really want. I honestly, it doesn't matter for the purposes of the summer course. Sydney and I were trying to remember if it was actually on a prelim. I remember it definitely being on a practice prelim, but if it was on our prelim, it was like one question that was worth like not very many points. Again, and we'll teach it to you again anyways. But the way
I don't believe we're going to be asking about this formula in any case for this course this summer.
Yeah, the only thing really you want to memorize from optical activity is going to be chiral molecules being optically active, achiral being optically inactive, so they do not rotate plane polarized light, and dexarotatory and level rotatory being clockwise and counterclockwise, or just opposite directions. Does that make sense?
Yeah, but I'm just wondering, like, what would you use that formula for?
I think on the practice prelim that we had for Ganem, where it had this, he just gives you a bunch of numbers. You remember in Gen Chem how they would just throw a bunch of numbers at you and you'd have to figure out what to do with them? Mm-hmm. It was a little bit like that with this equation, except honestly way easier. I don't have an example off the top of my head, and I don't think you should be super worried about it. If you want, I can find an example, and if you email it to me, I can like walk you through it, but it's not critical at all.
So the slide after that, I didn't understand how you came up with. So you said they were the same?
Yeah.
I don't see it because
I don't have. Do you have a model kit you can do with this, Sydney? I know the pentagon's gonna be whack, but I didn't draw on the hydrogens just because if you remember for skeletal molecules, you don't usually draw on the hydrogens. But if you just imagine a pentagon, sorry, I don't have a model kit, I can't show you. But if you imagine a pentagon with like the one deuterium sticking in, you could just as easily just turn the pentagon around. Like, just straight up turn this guy around. And then his deuterium would be sticking forward instead of back. Does that help at all?
Wait, I'm trying to visualize it. I guess, yeah. So it's just like you have to visualize it in your head.
Yeah, I mean, it helps when you have a model kit. Sydney, are you trying to talk? You're muted.
I was wondering why everybody was ignoring me. Sorry. This is a pentagon, and if you can imagine this blue, this is the deuterium. So when we say that the deuterium is on, I believe one of the problems it's on a dash, that means that it's like pointed in back, like away from the screen, like it's not coming. This, like right here, this looks like this would be what it would be as a dash. So I'm trying to figure out what it would look like as, I'm sorry, this is what it looks like as a wedge, like it's coming straight out at you, if you can see. I'm trying to figure out how I can show it as like a dash, doggone it. I think if I draw it maybe like this, like if it's coming away from you, imagine it's now like a dashed figure. Well, if you rotate it, then you're going to, of course, get the opposite configuration. Like you basically turn the wedged deuterium into the dashed deuterium, or vice versa. So to be able to tell whether those two molecules in that example problem are the same or different, like if you just, there's only, first of all, one non-hydrogen substituent. So this is the only thing that would make this molecule special. All these other points sticking up, these are all hydrogens. So the only thing we have on here is the deuterium that's different. So for the two examples, one of them is, I believe, a wedged deuterium, and the other one is a dash. Yes, one was a wedge, and one of them is a dash. So if I rotate the deuterium around, then I've just basically created the other structure, and I can superimpose them and it'll work just fine. That's why for some examples, a good idea is to try and flip the molecule before you try to superimpose it. You can flip it or rotate it and get the two molecules to line up perfectly, then you're good. Like, then it's the same molecule. If that makes sense.
Yeah, it's that is easier to see, like with the model too.
Yeah, as of right now, I'm writing the post on Canvas where I'm going to have my model kit linked up. Just for reference, right now it is the Molecular Visions organic model kit. I recommend like asking upperclassmen if they want to get rid of their model kits, just because I would not pay more than like $15 max for a model kit. You can find them for cheap online. I got mine for like $8. They're great to have, and I highly recommend. But yeah.
And visualizing the structures in your head will also get easier. I was lazy and didn't use model kit. Mine's an Ithaca. I stole it from a friend. But it does definitely help to start out with the model kit, and then from there you kind of get your own intuition.
Also, this is a little bit of a side note, but I will like demonstrate the cyclohexane chair flip with my model kit real quick, even though we didn't talk about that at all this lecture. This is a cyclohexane. It's got 1, 2, 3, 4, 5, 6 carbons in it. And if I flip it into a chair, it looks like this. So this is the headrest, this is the body, this is the footrest. If I go like this, swoop, then I've moved my axial substituents into equatorial, and my equatorial substituents into my axial substituents. Like watch this. This is axial first, and now it's equatorial. So that's another reason why I like model kits, because you can very easily visualize the cyclohexane chair flips that we learned on Wednesday. I'm sorry, on Friday, not Wednesday.
I actually have a question about the last practice problem that we did.
Yeah.
when we were trying to figure out if it was meso, diastereomer, all that. I was just wondering which of the isomers are like mutually exclusive to each other.
They're actually, as far as I'm aware, all going to be mutually exclusive. Where's meso on here? Yeah, don't worry about cis and trans for now. They'll talk about that, I believe, on Wednesday. But yeah, they're all going to be mutually exclusive. I don't know why meso is not on here. That would just be the stereoisomer. Does that seem right, Sydney? I just put them here.
Yes. You've got diastereomers and enantiomers, and you have, it's not on the chart, but mesos would be another one. The difference between diastereomers, enantiomers, and meso, sorry if you already said this, Samantha, is that the meso ones would be achiral because they've got the plane of symmetry. While the diastereomers and the enantiomers, those are chiral stereoisomers. That's probably why whoever created this graph didn't put meso compounds in there, but they're there.
Yeah, thank you for pointing that out, Lizette. I didn't even realize. Yeah, so they're all going to be mutually exclusive. Like Sydney said, they're probably just talking about chiral, didn't want to get things confused, hence why they left it out. But yeah, it can only be one of three things. Or same is also mutually exclusive, but of course that's not an isomer. So yeah, anytime you have a question that's like, is it the same? Is it a diastereomer? Is it an enantiomer? Are they meso? It's only going to be one of those options. Does that make sense?
Yeah, thank you.
Anyone else?
The Quizlet link, since many of you have been asking about that, I will put that in the discussion where it says resources that you can use if anybody's interested in checking that out, since I've gotten a lot of messages about that so far. It's also going to be in the discussion below for our YouTube watchers.
All right, if no one else has anything to ask, I think I'm going to go ahead and end the meeting. That's cool. If you have any questions, feel free to email me. Also, probably Sydney, I assume. Yeah. Yep. Have a nice day, everyone. Bye.